Welcome back. We're now going to talk about one of the most famous algorithms in all of artificial intelligence, and that is the A-star search algorithm. A-star is a heuristic search algorithm that is very powerful, and we will see in a moment why that is. It's using both the path cost and the heuristic values. And this is what allows it to lead to optimal solutions. It's making a decision based on the cost it took to get to a given node, as well as the estimated cost going from that node to the final destination. So you have the two components, cost P, which is that actual cost that we compute, and the heuristic function of P. And so we will use the notation f of p to indicate the sum of these two things together. So as you can see here, cost p is the least cost path from the start node to the node n that we are considering across path p, which is our least cost. And then h of p is the rest of the estimate of the rest of the journey going to the goal. And so what happens is our frontier set of nodes is now being set up as a priority queue, and instead of picking from that priority queue with using h of p, like we did with best first search, we are going to select using f of p. So more information. And so it's always going to select the path on the frontier with the lowest estimated cost from the start to the end, to the goal node. Whereas before, we weren't considering from the start, we're just considering from the current node in the frontier to the goal. All right, so here we're going to show a little example of A-star search in action. So again, we have written on the next to the nodes the heuristic value to the goal, where G is the goal. So you see here, node E, even though there's no path to the goal, it's got a straight line distance of 3, and that's our just heuristic underestimate of how far it takes to the goal. On each of the edges, we have the cost to get to that, or to traverse that edge. So let's start at node A again, and let's travel through this using A star. So we have our node, and we have our f function, okay? So we have 3 selections. We can go to node B, which we have a 2 plus a 5, and that's a 7, so that's for B. We have C, which is 3 plus 9, which is 12. And we have D, which is 4 plus 6, which is 10. So we pick B to expand next. Okay? So we have 2 options there. We can go to node E or F. Well, the cost for E is going to be 4 because we have got 2 and 2. So we've got both those 2's, and then we've got a 3 for the heuristic function there. So these are your cost, and this is your H, okay? So altogether, that makes a total of 7 for E. All right, likewise for F, we do the same thing. 2 plus 3 is 5, and 5 plus 5 is 10. So for F, we have a value of 10. Oh, and by the way, since we expanded B, we can eliminate that from our priority queue. All right, so the lowest thing in our priority queue is going to be node E. Now, here we see right away, since there's no out edges, E has an actual infinite cost to node G. There's no way it can get there. So we now have updated E to be something that we can't use. And so we can drop E from the priority queue. All right? So let's put a X on that. All right, so what do we pick next? Well, we can either pick D or F. And so it would just be a coin flip at this point, because from the perspective of A star, we have underestimates for both, okay? So what we got, let's say we pick F. And so we pick node F, and we have, the heuristic cost to the goal was 10. Now this adds node D to our priority queue. Well, if we look at the path to node D through nodes B and F, we have now 2, 5, 7. 7 plus 3 is 13. So I'm going to put this in a different color here. This is going through B and F. Now, that gives us some information right away, because the F function to get to go through node D starting right at A is much cheaper than if we went through B and F. And so we can ignore those guys, and we can now hit D right through node A. So we can eliminate F because that doesn't give us any cheaper options than what's left in the priority queue. So we can get rid of that as well. So, okay, we go to node D, and going to node D, we now have added node H to the priority queue. And H, the cost to get to the goal through H is going to be 11. Let's erase that from before. All right, so we have node H. Then what do we add next? Well, we add G. So going to node G through H. Now, it turns out that to get to node G through H, we have a cost of 11. And there is nothing else left in our priority queue that has a lower value than 11, and that's because H is fully expanded at this point. So now we have a solution. We go from A to D, D to H, and H to the goal. And it turns out this is optimal, and this stems from the fact that our heuristic function is an underestimate. So you can think of this as a mix between lowest cost first search and best first search. In fact, it's adding both those together. To recap, we're treating the frontier as a priority queue, and we're always selecting the node with the lowest estimated cost from the start node, constrained by that route. So, does it guarantee to find a path with fewest arcs? Well, the answer here is yes, in the case where we're considering cost to be the number of arcs. If we consider cost to be something else, that's not necessarily going to be the case. It does guarantee we find least cost path under certain assumptions, and we'll kind of touch on that. Infinite graphs and graphs with cycles, it's still not going to terminate. We're still going to run into some of the same issues that we've had before. And unfortunately, even though the heuristic function in practice will give us reduction in time complexity, we're still going to have, it's still going to be exponential in the worst case. The trick is we want to reduce what we need to expand by having a really good heuristic function. And the same here goes for space complexity. And so we see kind of a summary, and we'll bring this up again in a later lecture too. But, you know, when you're looking at A star, it's not guaranteed to halt unless you're doing some additional stuff to prune cycles and redundant paths. It is complete, however, especially under for finding the lowest cost path, and this is under the assumption that your heuristic is indeed a lower bound. But again, space can be a problem here. So that's it for now on A-star search. Stay tuned as we continue the discussion.